So here we go, trying to find an interval of convergence all the way through. We have our series right here, n is equal to 1 and heads towards infinity, and we have 3x minus 2 to the nth power over n. So we want to find that interval, so we're going to start with the ratio test. So we have the limit as n approaches infinity, and it's going to be the absolute value of 3x minus 2 to the n plus 1th power over n plus 1, and we're going to multiply that by the reciprocal, or n over 3x minus 2 to the nth power. That absolute value, that limit, must be less than 1 in order for the ratio test to give us the convergence. Okay, so what do we do? Same thing that we've always done with these n plus 1s. This is really 3x minus 2 to the nth power times 3x minus 2, which allows us to eliminate both of those. And just like our previous example, we can pull our n's out. So we end up having the limit as n approaches infinity. We have n over n plus 1. And then in the absolute value, we have 3x minus 2. That must be less than 1. Now we look to calculate this limit right here. The leading coefficient, well, the degree is the same in the numerator and the denominator. So we focus on leading coefficients. They're both 1, so that limit is equal to 1. So we end up having 1 times this, which means we're looking at 3x minus 2 is less than 1. Now to get our interval, we're going to split it up. So we are now looking at 3x minus 2, and that's going to be either greater than negative 1 or less than 1. Okay. What do we do there algebraically? Add 2, divide by 3. So we're looking at 1 is less than 3x is less than 3, and 1/3 is less than x is less than 1. All right, so here's our initial interval right here. But what we don't know at this point is what's going on with the endpoints. All right, so we have to check out what happens if x equals 1/3, and what happens if x is equal to 1. All right, where do you want to start? 1/3? All right, so if x is equal to 1/3, means we're going to go back up here, and we actually want to put in 1/3 for x. All right, and if we put in that 1/3, then we have 3 times a third, which is 1, minus 2, so it's negative 1. So what we end up having is this series, negative 1 over n to the nth power. All right, so if x equals 1/3, we're looking at the sum as n equals 1 to infinity of negative 1 to the nth over n. What's the name of that series? Yeah, it's the alternating harmonic. All right, and we know, we've already proven many moons ago that the alternating harmonic is a convergent series. All right, so this series converges, all right, by the alternating series test, technically. All right, we don't have to list that, all right, but it's true. Okay, so this converges, which means that we need that little mark right there because the series converges when x equals 1/3. What about when x equals 1? Now we go back here, and we're going to replace x with 1. And when we do so, we no longer have negative 1 to the nth power over n. We just have 1 to the nth power over n. So if x equals 1, then now what we're looking at here is the sum as n equals 1 to infinity of 1 to the nth, which is really just 1, because 1 to any power is 1. So we have 1 over n. What's that series? Yeah, that's the harmonic series, and we know that that diverges. All right, so this diverges, technically diverges by p-series. All right, so our p-series test tells us that it diverges, which means that the 1 is not going to be included as far as our endpoints are concerned. This ends up being our interval of convergence.